I'll just point out that surface tension in practice is often a lot more complicated than we show it in textbooks, and it's big business also. So like one of the big examples I think of where surface tension is actually used technologically is in heat pipes. So heat pipes are the things that actually draw heat away from your computer processor or other electronics, especially in smaller electronic devices like iPads and like laptops, small desktop computers. And so the way they work, for example, is that you can think about them like a cooling system where you are boiling off water in one location, and you have basically a hollow tube that's surrounded by porous material on the outside of the hollow tube. So so basically, after you boil the water or whatever fluids in the heat pipe, it is able to travel down the center of that hollow pipe and then condense somewhere else where it's cold. But then you need to be able to get the fluid to go back to the boiling area so that you can repeat the cycle. And that's where porous materials come in. So typically what they do is they take copper powder and sinter it together to create sort of a porous metal network that draws liquid very quickly through that copper sheathing back to the origination point for boiling. So these things are actually really cheap to make. Like these things don't cost more than $1 each when made in mass production manner, but still the market for them is like $16 billion because of how many electronic devices there are. So heat pipes are big business. You may have also seen like capillary forces being used in places like evaporative humidifiers. So there's a lot of actual technologies where wicks are used to suck water up into an area where then you want to get rid of it by blowing it. So like evaporative humidifiers is one common way that you see in like household electronics. So if you have a humidifier, there's probably about a 30% chance it works off a wicking mechanism. And of course, wicks are used for other things like candles and all sorts of things where you want to get a fuel from one location to another. Wicking is also used in cleaning products, so that's the name of the game for like a paper towel. There's a little business down the road called W.L. Gore that makes all of its money, I believe almost all its money, off hydrophobic materials. It's a multi-billion-dollar business. And basically the name of the game is putting down things like Teflon, which are very strongly repulsive to water, onto usually textured surfaces. So I didn't go into a lot of detail, but it turns out if you can get a droplet to sit on basically a coating of air, so like often what people will do is they'll create like Teflon pillars and try and make sure that there are spots where air touches the droplet underneath. That'll tend to make the water want to bunch up into balls or droplets a lot more. And so making surfaces that are both coated in hydrophobic solids, but then also trying to get some pore space to them to increase that effect is big business. And then lastly, as an example, is microfluidics. So a lot of like diagnostic tests these days are done on what are called lab-on-a-chip devices, where you create basically disposable chips where somebody pipettes, say, your blood or some other biological fluid into a reservoir, which is connected to a bunch of capillaries that sort of draw in your test fluid, do whatever tests they're going to do on them. So I'm just guessing, but if I'm looking at this picture, it looks like they've got a couple of wires going in to maybe 4 different leads. These people might be measuring the electrical resistivity or some such. But often capillary forces are used as a way to move fluid from one location to another so that they can be measured. So like designing doing the micro patterning and making sure you're using the right dimensions and types of materials is sort of big business.